Okay, so this is going to be the first of two videos on the topic of sampling, which is a really important concept, not only in this class, but also in ECE 101. It's actually the transition between ECE 45 and ECE 101. Is 101, you talk about this thing called discrete time, and the way you get to discrete time from continuous time is by sampling. So that's what we're going to talk about today. So we're going to talk about sampling a signal. In the next video, we're going to talk about whether it's possible to actually recover your original signal from its sampled version. And if so, how can you actually go about doing that? And I know that probably doesn't make sense right now, but after the next video, it will. So that's what these next two videos are going to be about. So, all right, so just sampling a signal for now. What's the story? Well, we're going to start with an analog, as we say, which is just another way of saying continuous time. Some people use the word analog, continuous time signal. Okay, that's what we're going to start with, and I'll just draw just a random signal so we have something to look at. Okay, so let's say it looks something like that. Let's say that's my x of t. Okay, and what do we want to do with sampling? Well, we want to turn x of t into a discrete time signal. Discrete time signal. Okay. And I'll show you more about what that means in a second, but this is the first step. You might say, why would we want to do this? Well, it turns out this is the first step to storing x of t on a computer, for example. Okay, so let me just draw what we want to kind of accomplish here, and then we'll talk a little bit more about it. But actually, let me just grab my same x of t. Okay, let's put it there. And so what do we want to do with sampling? Well, the problem is if we wanted to store this x of t on a computer, I can't store the values of x of t for every single point in time. There's too many points in time. It's an uncountably infinite collection. Okay, any real number t, I could plug into x of t and get a value. I could get a value there, I could get a value there and there. No matter what value of t I plug in, I have to store x of t for that value, but there's just too many. I can't possibly store that many values on a computer. Okay, and so what we want to do in sampling is actually only keep around some of the values. Okay, so we're only going to keep these values of my original signal, the red ones, and nothing else. Okay, so we're going to get rid of x of t everywhere else, and we just want to keep those values of x of t. This is the first step to storing x of t on a computer, because now we've gone from having an uncountably infinite number of values for x of t we have to store to only storing, I don't know, however many red dots there are, maybe 15 or so. Okay, so now we can store these values on a computer. The next step, which we're not going to talk about in this class, you can take other classes on this, is to say, well, wait a second, I still have this vertical axis, which also has uncountably infinitely many values here. And what you do then is you actually break up this vertical axis into different values, just some set of different values, and that's called quantization. Okay, so maybe that value right here in between those lines, I wouldn't actually store that value, I'd store kind of the line that is closest to it. So that's called quantization. We're not going to talk about that in this class. We're just going to talk about breaking up the time axis, breaking up the vertical axis, the amplitude axis is quantization, and that would be for a different class. Okay, so that's why I just said the first step to storing on a computer. First step is you break it up on the time axis. You discretize the time axis. We don't store the x of t values at any point in time. We only store them at these points in time corresponding to the red values. Okay, and that has now made our task for storing the signal on a computer a lot easier. Okay, so we just write the red values will be the only the only values of x of t that we keep when we move to discrete time. Okay. So what does continuous versus discrete mean? I mean, continuous is what we're talking about here, an analog signal. You can plug in any real number t, versus discrete time, you can only plug in these values. Okay, you can only plug in these values of t corresponding to the red dots. Okay, and so this is a discrete collection of points on the time axis, and that's going to be our discrete time. Okay, so that's what we're trying to accomplish here, and this is the transition between 45 and 101. Okay, so the question is, how can we actually do this? How can we convert continuous time signals to discrete time and analyze them? How can we do that? And that is what the process of sampling does. Okay, so that's what we're going to talk about. Sampling is the process of taking a continuous time signal and sampling it, only looking at it at certain locations, only keeping around certain values of that signal. Okay, that's what sampling is. So how are we going to do this? Well, it turns out that we're going to use impulse trains. Okay, we're going to use impulse trains to create a sampled version of x of t. So let's just review what an impulse train is. Okay, definitely rewatch the video on impulse trains if you forgot. Okay, so I'm going to call it s of t, my impulse train, and I'm just going to take it to be this sequence of delta functions. And I'm just going to have them all of height 1. This goes on forever. Okay, they're all going to have height 1, and they're going to be periodic with period t sub s. Okay, so this is an impulse train. Okay, and how would I write that mathematically? Well, it's just a big sum of deltas. It's the big sum of deltas, where all these deltas still have height or area 1. They're just shifted. I'm going to shift them all by integer multiples of t sub s, and this t sub s, what do we call that? That is what we call the sampling period. Okay, it's the period of our impulse train that we're going to use for sampling. Okay, and we also saw, and we're going to care about in this video, the Fourier transform of an impulse train. Okay, and it turns out that that was another impulse train. Okay, and how is this impulse train related to the first one? Well, this one now has its heights scaled by what I'm going to call omega sub s. And it's also periodic with period omega sub s. And that omega sub s, which is 2 pi over t sub s, is going to be the sampling frequency. Okay. And actually, wait, I also wanted to write mathematically what this function is, so I'll move this down for a second. Okay, so that's what we call the sampling frequency. So for periodic functions, we have the period and the fundamental frequency. For these impulse trains, particularly in the context of sampling, we're going to call the period of the impulse train in time the sampling period, and the fundamental frequency, okay, the sampling frequency, which is the period of the Fourier transform of our impulse train, which itself is another impulse train. So what does this look like mathematically? Well, it's still just going to be a big sum of deltas. It's an impulse train. The deltas are all shifted to integer multiples of the sampling frequency. Right? You can see that omega sub s, 2 omega sub s, 3 omega sub s, and so on. And they're all also scaled by omega sub s. So we saw this in the impulse trains video, and we proved all this already. So we can just use it now. Okay, so that's our setup. And what are we going to do? Okay, well, we will periodically, specifically with period t sub s, the sampling period, we're going to periodically sample a signal x of t at integer multiples of that sampling period T sub s. Okay, so in this picture, it turns out I'm going to sample this value at 0, and the next value is going to be at T sub s, the next one at 2 T sub s, and so on. And I'll draw this picture again in a second, don't worry, but that's how it relates to the red values we talked about earlier. Okay, and so how are we actually going to do this? I'm going to kind of use this moment to describe what we're going to do, so we're all on the same page, and then I'm going to actually do it. So we will do this by creating a sequence of delta functions. Sequence of delta functions whose heights, but remember, the heights are actually the areas. We talked about this in the delta function video. Whose heights or areas are actually going to be the values we care about, or the values of x of t at the points n T sub s, so integer multiples of our sampling period. And so that means, so we will be keeping the values x at these integer multiples of the sampling period locations. We're going to be keeping those values. Okay, so this is exactly what I showed before with the red dots. It's just our signal is not going to equal these values at those locations. We're actually going to put delta functions whose heights are those values. That's going to be our sampled signal. Okay, and these are going to be, again, at integer multiples of the sampling frequency, or sorry, sampling period. Okay, so that's going to be our sampling signal. We're going to have a sequence of delta functions whose heights or areas are the values of x of t we care about. So this would be scaled by like x of 3 times T sub s. Okay, and don't worry, I'm going to draw all this again. I just wanted to connect it really quickly so we're on the same page, and then we'll do it all out in more detail. Okay, so that's what we're going to do. And the reason we make these values be scaled delta functions instead of just, having those values themselves, sort of, is that we want to be able to recover these values via integration. So we know if we integrate that delta function, we're going to actually get the value of its height or area, right? Which in this case would be like x of 2 T sub s. And that's useful to us to represent it in this way, because now if we integrate this function, right, from there to there, we can actually recover this value x of 2 T sub s. Okay, so that's how we're going to discretize our signal. We're going to represent it as a bunch of deltas whose heights or areas are going to be the values of x of t at those points. So that's our goal. But the big outstanding question is, all right, that's great, but how can we actually do this methodically and mathematically so that we can be precise about everything? Okay, how can we do that? And to show you, I'm going to kind of get all the materials we have. So I'm going to draw, I don't know, let's just say our x of t function looks something like this. Okay, just random. I'm going to take this to be my x of t. Okay, and now what we're going to do is we're going to use an impulse train to sample it. So let me draw the impulse train. Okay. All right, so this is going to be my s of t. I'm going to take all these deltas to have height or area 1, and they're going to be located at integer multiples of T sub s, the sampling period. Okay. And now what do we want to obtain? Well, it's going to be the picture that I drew before. What we want to get in the end. Okay, let me actually draw this bar a little higher. What we want to get in the end is a sampled signal, which I'll represent as x sub s of t, so the sampled version of x, which we want to be these delta functions. I'm trying to draw this as best I can here, that are now kind of scaled by the values. Maybe this, shoot, I don't want to do that. Let me move these over a little bit so it lines up a little nicer. Okay, so this is -2t sub s, -3t sub s. Just wanted to have that one actually hit our functions. Maybe it looks something like that. Okay. So we have all these delta functions at these locations. So at integer multiples of the sampling period. Okay, and their heights are going to be the values of x of t at those locations. So we're going to be picking out these values, okay, of x of t, which we can see have values like x of 0, right? This is t sub s. This is going to be x of t sub s. This is x of 2t sub s, and so on. This is x of negative t sub s. Right? We're going to pick out all those values and use those to scale these delta functions. Okay, this is x of negative t sub s. And what's really happening is that our original function is kind of following, okay, these deltas, but I'm drawing it as a dotted line because it's not really there. The only thing that's there is actually those delta functions, but you can see I've used the values of x of t to scale the heights or areas of those deltas. And so that dotted line would fit perfectly with those delta functions. Okay, so this is the picture of what's happening. I hope it's clear. We have x of t, we have our impulse train. And then what we want to create is this is our sampled signal down here. And we're going to represent that sampled signal. How are we going to represent all of these values of x of t we want to keep around? We're just going to use those to scale the delta functions in our impulse train. Okay, this is going to be our sampled signal. Okay, let me actually move this down a tad. Let's get this out of the way a little bit. Okay, so that is our sampled version. Let me just write that. So the sequence, say this sequence of scaled deltas is our sampled signal, x sub s of t. Okay, that's what it is. And what does this look like mathematically? Okay, well, we can write it down. It's just a big sum of all these delta functions that are located at integer multiples of our sampling period. And the question is, what are these delta functions scaled by? You can see the delta function located at 2t sub s is scaled by x of 2t sub s. The one located at t sub s is scaled by x of t sub s. So the one located at n t sub s is just scaled by x evaluated at that location. Okay, so you can see that these are kind of all of our samples, and we just want to make sure that those values are located in the correct location. So we multiply delta functions by those values that are located at the corresponding locations. Okay, so hopefully this all makes sense. Now the big question is, all right, that's all good, but is there a way for me to write x sub s, the sampled signal, in terms of x of t and s of t? Because right now that's not really clear. Like I wrote this thing down, but they haven't really said, is there a way to write this cleanly in terms of x and s? And it turns out there is, so let's just manipulate this equation a little bit. So if I have x of a value times a delta function at that location where I'm taking that value, okay, I can actually write this just as x of t times delta of t minus nt sub s, right? We saw this with our delta function properties. I have a function x of t and I multiply it by a delta function. I just get that same delta function, but now scaled by the value of x at the location of the delta function. Okay, so we saw that previously in the delta function video. But now x of t doesn't depend on n, so I can bring it outside. I'm left with these deltas. But now what are those deltas? Where have we seen that before? Well, that's exactly my s of t signal, right? It's just a bunch of delta functions shifted to be at integer location in integer multiples of the sampling period. Okay, that's exactly what I have here. That is what this is. Okay, this is my s of t. And so I just end up with x of t times s of t. That's it. So our sampled signal is just taking x of t and multiplying it by this impulse train. How nice is that? And you can see that pretty clearly, right? If I took x of t and I multiplied it by this whole impulse train, certainly the result will be 0 wherever I don't have a delta function, right? Because the zeros in this impulse train are just zeroing out whatever x of t is there. And then at any point, let's take this one, for instance, at 2t sub s, I'm just going to have that delta function times this value, right? That's what we did in the delta function video to get this property. Okay, so when I take x of t and multiply it by this delta, I just get that delta function scaled by the value of x there, right? And then you just do that for every single delta, and there you go. You have your sampled signal exactly, x of s of t, and it's really simple. It's just a product. So we just want to multiply x of t by the impulse train s of t. That's how we sample. Isn't that really nice? So impulse trains are really useful. This is a nice, clean answer. Okay, so that's great. So that's what's happening in time with our impulse train. But a big question is, how has the Fourier transform of x of t, how has the Fourier transform of x of t changed after sampling? Okay, i.e., the big question is, how are x of s of omega, or sorry, how are x of omega, the Fourier transform of x of t, how are x of omega and x of s of omega related? Okay, is there a way to understand their relationship? And of course, this is just the Fourier transform of our sampled signal. Okay, so is there a way to understand how x of omega and x of s of omega are related? And it turns out there is. Okay, so let's just compute that Fourier transform, and we'll see. Let's compute x of s of omega. Okay, so x of s of omega is the Fourier transform of x of t, or sorry, x of s of t. Okay, which is the Fourier transform of x of t times s of t. That's what we just found. The sampled signal is our original signal times our impulse train. How do we take the Fourier transform of a product? We saw this in the previous video. We can use the multiplication property of Fourier transforms and say, well, okay, the Fourier transform of the product, that's easy. It's 1 over 2 pi times the convolution of their Fourier transforms. So the Fourier transform of x of omega, we have no idea what that is. Okay, that's just some arbitrary signal. But the Fourier transform of s of t, s of omega, we know. It's right here. Okay, we know what that Fourier transform is. I'll just copy it. Okay, so that one we know. And now we can use some convolution properties and say, all right, this constant, that's fine. I can pull that outside. Okay, convolution is has that scaling property. So I write this as omega sub s over 2 pi. Okay, and what am I left with? I'm left with x of omega involved with this impulse train here. Okay, and what else can we use? What other properties of convolution? Well, right now we have x of t convolved with a big sum. We know that convolution is distributive. Convolution is distributive. Okay, and so I can actually distribute that x of omega into the sum and say x of omega convolved with a sum is really just the sum of the convolutions. Okay, this is a good review of a lot of useful convolution properties. So what do we have now? Well, x of omega convolved with a shifted delta, what do we get? We also saw this before in a previous video. That just shifts our function x of omega by that amount. That's it. That's what happens when you convolve with a shifted delta. And then one more thing I'm going to do is just write omega s over 2 pi. What is that? Well, 2 pi over omega sub s is a sampling period, t sub s. Okay, so this is the reciprocal. This is just 1 over t sub s. Okay, so this is what happens to our Fourier transform x of omega after sampling. Okay, how can we summarize this? Well, it's actually pretty interesting. So the Fourier transform of our sampled signal, what is it? It's actually an infinite sum of scaled and shifted copies of x of omega. So this is the huge takeaway that you're going to learn again in 101, but this is kind of the main point of what happens in the frequency domain when you sample. It turns out that the Fourier transform of your sampled signal is actually an infinite sum of a bunch of shifted and scaled copies of your original Fourier transform x of omega. Okay, so it's really strange that that happens, that when I sample my function, when I multiply it by this impulse train of deltas, okay, and I just keep around the values of x of t at certain locations, multiplied by delta functions at those locations, what happens in the frequency domain? Well, we actually get a big sum of shifted copies of my x of omega, my original Fourier transform, all scaled by 1 over t sub s. Okay, so let's look at a specific example to see what this looks like visually. So I'll just take a random example. Let's just say x of omega happens to look like this, just so I have something to draw. Okay, let's say it happens to look like this. Okay, just sort of a triangle and a square. And for the purposes of this example, let's just take some values. Let's say the sampling frequency is 3. And so the sampling period is 2 pi over 3. And now let's just draw what would happen in the frequency domain when I sample the signal with this sampling frequency and sampling period. What would happen? Well, let's look. I'm going to get a bunch of shifted copies of x of omega, shifted by integer multiples of omega sub s. So let me draw those in first. So this is going to be omega sub s, which is 3. This is 2 times omega sub s, right? I'm just writing out all these integer multiples. I'm -3, -6. Okay, and what do I get there? I get shifted copies of my original x of omega. So I just have to shift this x of omega by these amounts. So I get one when n is 0. I just get x of omega itself right there. And then I get a copy at 3. I get a copy at 6. I get a copy at -3. I get a copy at -6. Okay, so I just get this big sequence of these shifted Fourier transforms, but they're all also scaled by 1 over t sub s. So that value right there is 1 over t sub s, which is in this case just 3 over 2 pi. Okay, so this goes up to 1, -1. This is 1 less than 3, right? Just 1 to the left of that center point. So this is 2, this is 4, this is 5, this is 7, -2, -4, -5, and -7. Okay, so that's what happens when I sample. It's kind of crazy. Whatever x of t looks like, I've sampled it to get x of s of t, and this is what happens in the frequency domain. My original Fourier transform, what happens when I get the Fourier transform, my sampled signal, I get a bunch of copies of my original x of omega shifted to these integer multiples of the sampling frequency and scaled by 1 over t sub s. Okay, so x sub s of omega is actually periodic. Okay, x of omega is clearly not periodic, but this function now, after sampling, is periodic. Kind of interesting. Okay, so the way people remember this is just to say the Fourier transform of the sampled signal. What do you get? You get an infinite collection of these these shifted copies of x of omega that are all scaled by 1 over t sub s. Okay, so this is what it looks like in a picture, and we're going to be seeing a lot more of this in the next video when we talk more about sampling. Okay, so great. So this video is just about the process of sampling. The next one is going to be about potentially trying to recover our original function x of t just from its sampled signal. Okay, so right now we've gone from x of t to the discrete time version to x of s of t. Is there a way that we can actually go back? Okay, is that possible? And if so, how can we do it? So that's what the next video will be about. Okay. So So great. That's all I have for this video. I'll see you in the next one.